Anyway, yeah, when I was looking at those diagrams, I mean, I'm thinking, gosh, alpha decays, boy, they just get in the way of everything. They are actually one of the major backgrounds in my experiment. So always worth knowing a little bit about. Anyway, okay, so as I said, well, you shouldn't call it as a promise that we'll do only simple things today, but we are going to get just a tiny bit closer to physics, right? Because last week we were mostly talking about math. So we're going to, a lot of the stuff that we've been talking about has, gosh, there's so much more echo in this room today. I wonder what's different. Anyway, right, so last week, of course, we were covering a lot of stuff that's related to geometry. And just at the very last moment, we sort of narrowed ourselves down to 3D Euclidean space. So let's stay there for just a little bit. So we'll do Euclidean 3D physics vectors. Okay, or physics objects. We'll get to other things pretty soon. The vectors are pretty well known. Of course, you have things like, position, right? Momentum. Oftentimes, for some reason, we use u for velocity, but obviously these are just names. Okay, no big deal, right? And then you also have things like force. A couple other ones. Perhaps slightly, I guess you've seen this, you started seeing this last year, where we would actually talk about the current as a three-vector. And you've also seen angular velocity, and angular momentum, and finally, torque. Okay, so all these things should be quite familiar to you from good old 3D mechanics. And just to sort of get this back to that discussion of symmetry, or since we've been talking about symmetry, remember we're always talking about something. We're talking about a transformation. Oftentimes, and what we sort of narrowed ourselves down to were orthogonal transformations, at least in the case of Euclidean geometry. So things like rotations and space inversion. Now, obviously, the vectors themselves, right, the components, they do change when you rotate. But there are various things that don't change, like the length. Okay, so that's invariant. The other thing that would be invariant would, of course, be relationships. So, for instance, if you took Newton's law, right, oftentimes written F equals ma. Okay, now in our sort of, wonderful component notation, we'll do that, right? And we can apply a transformation to this equation by multiplying by the transformation matrix. We'll say lambda ji, fi is equal to m lambda ji I, okay, and then sum over I, right? And of course, we recognize that this thing is simply the transformed force, F bar j, and this one is simply the transformed acceleration, so A bar j, okay? So we get the relationship F bar j is equal to m times A bar j, or in other words, the equation, right? The equation itself stays the same. Equation stays the same with respect to rotations and things like space inversion and so forth and so on. The orthogonal transformations. Okay, so this would be an expression of symmetry in the sense that you've done the transformation and you get the same equation back. Okay. Now, let's see. So those were vectors. Now, we had introduced the concept of the tensor last time. So you probably are wondering what kind of tensors might we run into. So one, of course, that I think we did kind of touch upon this. Now, you'll have to sort of trust me a little bit on this first, because actually we're going to write angular momentum again. But we're going to do it in this form. So Lij is equal to xi pj, the three vectors, and then xj pi. Okay? Right. Now, so this is actually going to be, well, it's obviously a rank 2 tensor. But in particular, right, if you swap the I and the j indices, you pick up a minus sign. So this is a rank 2 skew-symmetric tensor. Okay. Now, when you look at, I mean, if you were to actually write out all these components and then sort of stick it into a 2x2, I mean, into a matrix. Okay. Now, remember, the matrix is not the tensor. We're just representing the components this way. So I'm being just slightly casual when I write Lij. I don't know if there's a special symbol for just, like, well, anyway, yeah, equal is, yeah, we'll just go with that right now. Anyway, so you get a 0 in the diagonal. Now, let's see. So this one will be L12, right? So that will actually be Lz, okay? And you get these other components like this, okay? And then, of course, it's skew-symmetric, so you got to have a minus sign on the other side, right? Okay, so this is what the components of the skew-symmetric tensor look like. Now, notice there are actually only 3 degrees of freedom here. Okay. So only 3 degrees of freedom in Lij. Okay. That is very much like, of course, the fact, I mean, that's very much like a 3 vector, okay? Which, of course, you've also seen, and generally you will have seen angular momentum written down as a 3 vector. So oftentimes what people would do is do something like this. Well, in our notation, x cross p, okay? Or, if you want to use components. Now, remember, this is Euclidean space, so upper and lower components, not really a big deal. So I'm just going to do a lower component there for convenience. Oftentimes, you would see this written like this. Okay? So you might wonder, what in the world is the relationship between the rank 2 tensor and a rank 1 tensor, both purportedly describing the same thing? Well, it gets worse. Okay, just to make sure you feel extra uncomfortable about it, because the transformation rules are quite different for these kinds of objects, right? Because if you remember correctly, if you have a 3 vector and you want to transform it, then that just looks like this, okay? Whereas if you have a rank 2 tensor, it's going to look more like lambda j b, and then you have L A b, okay? So you have 2 transformation matrices here instead of 1 transformation matrix. Okay? So you might be wondering, have we just been, pulling your leg all these years? But you can, well, basically be a little bit more explicit about this and see what happens. Okay, so let's actually do a transformation. I mean, now we know how to transform a 3D vector, so I'm assuming you don't need to really write that down. But in the case of the tensor, this one's a little bit less familiar. We have 2 matrices, and this one we're just writing as a matrix. But of course, to do that, you realize that, let's see, we have lambda IA LAB. Okay, so that's just to get the two indices next to each other so it looks like a matrix multiplication. Then here, of course, you have a little problem because that's the wrong index, but no problem with that. We're actually in matrix notation, we're just going to write this as lambda L and then lambda transpose. Okay, and that puts our indices in the right place. Okay? So let's try that. Let's do a rotation around the z-axis. Okay. So you can have cosine theta minus sine theta, cosine theta. Actually, what I should have done is write this as sort of like an exercise for you guys to do at home instead, but you can fill in the details if you want to, because I'm not going to do absolutely everything, because that'll just take too long. Okay, so we have our here, and then of course you have the corresponding transpose over here, so cosine theta, sine theta, minus sine theta, cosine theta, and then 1. Okay? Now, if you multiply this out, what you should get is, let's see, first a 0, then a minus LZ, because of course the, LZ shouldn't change. And then you'll have Ly cosine theta plus Lx sine theta. Okay? No surprise, this guy should still be Lz. That will then be that. And then we have Ly sine theta minus Lx cosine theta. Okay? And then, of course, we have the corresponding terms on the other side, minus y, Ly, et cetera, et cetera, et cetera. I'm not going to bother with that. Okay? Okay, because you know that it is an antisymmetric arrangement. Sorry, so these are separate components. Okay? And so you can work out the details for yourself, but I mean, if you actually go through this, through this multiplication, what you'll find is that, this thing will be sitting in the position of Ly, of the transformed Ly. This one will be in the position of the transformed Lx, or minus that. And what you'll find, of course, is that it transforms in exactly the same way that you get with the vector. Okay? So at this point, it just sounds like a more complicated way of doing a rotation. But there's one other thing. Now consider space inversion. Okay, so now we're going into the realm of the improper rotations. In that case, the transformation matrix looks like this. Okay, and so from this you can see fairly quickly that if you had a 3 vector, then this is clearly going to invert all those elements. But if you had your nice skew-symmetric rank 2 tensor, actually you will find, well, because it's actually, actually this thing enters twice, right? So actually this does not change, doesn't change sign. Okay, now which one is correct? Right? It's actually this guy. This is the guy. I mean, because if you go back and think about what that original definition meant, x cross p, this thing is not supposed to change sign. It is in fact what we call a pseudovector, sometimes called an axial vector. Okay. And yeah, the thing is that when you do space inversion, this does not change sign, unlike a regular vector, which would. Okay, so this is a little bit like when we were talking last week about the Levi-Civita symbol and whether it behaved like a tensor, a proper tensor or a pseudotensor. The pseudotensor meant that it actually had the opposite sign behavior when you flipped the coordinate system. I mean, when you reflected the coordinate system. Okay? So, yeah. So it actually turns out that the rank 2 skew-symmetric tensor is actually a more natural way to represent, is a more natural representation of a pseudovector. Okay? Right. Okay. Now, let's move on a little bit. You might think, okay, so that's great for a rank 2 and skew-symmetric tensor. Is there any example of a rank 2 symmetric tensor? Okay, so one example is something called the stress tensor. Okay, oftentimes denoted sigma ij. And this is something which, it actually comes up in a couple different fields. Engineers use this a lot. Certainly things for static, analysis of static systems, elasticity, as well as fluids. Okay, and in fact, I think in B1, I think you may run into the stress tensor, but possibly just as kind of like, oh, this is an interesting way of writing the equations. Okay. Now, the way the stress tensor, the way to think about, to get a picture of what a stress tensor is doing, maybe fluids is probably the easiest sort of picture. You can think of, some sort of volume, some fictitious volume, and you have a bunch of particles flowing through it. Okay, and it might be doing various kinds of things. And so you can think of the stress tensor as the flow of momentum across one of these surfaces. Let's just focus in on just one of those vectors, right? So if you had a particle sort of, being transported across one of these boundaries, so if this was, say, the x direction, and this was the y direction, and this would be sort of px and py, you sort of know that So py exerted on the y face, that's basically a pressure, right? Okay, so it's something directly sort of applied to the face of the volume. But so this guy, in this case, going across the y face would be a pressure, or would act like a pressure. Whereas the px, this would act, because this is actually going along the surface, that's actually what we would call a shear stress. Okay, so if you were to represent the, if another illustration, just in case it is more helpful, is that if you put your hand on a table, right, pushing directly down is the pressure, but trying to sort of push it along by sort of exerting force on the top, that would actually be, you're actually using the shear stress to be able to push the table along. Okay. So if you were to think about this in the matrix form, the diagonal elements would be the pressure, and then the off-diagonal elements would be the shear stress, also over here. Okay. Now, this is actually, I should correct myself or adjust this a little bit. It is only in equilibrium, right? Only in static equilibrium that this is a symmetric tensor. Okay? If you're not in equilibrium, then you actually have 9 whole degrees of freedom. Okay? Yeah, okay. But anyway, we'll leave that picture just for now because actually there's a somewhat more, or at least what I find to be a slightly more intuitive symmetric rank 2 tensor is actually the moment of inertia. Okay? Now, you remember this from first year, of course, and we did not really tell you at that time that this was, in fact, a rank 2 tensor, because that just would, that would be just like inappropriate language in the first year. So we can, take this over a rigid body. Here's mass density, and then you have this, what you're actually integrating over, delta ij minus xi xj, okay? So this is the definition of the moment of inertia as a tensor. And you can see that, if you were to switch the I and the j, you get exactly the same expression. So this guy is supposed to be a rank 2 symmetric tensor. In this case, I think, just to give an example of then how this transforms, because there's something that is a little bit interesting coming out of this. You can oftentimes envisage the moment of inertia tensor as sort of taking a three-dimensional rigid body and sort of collapsing it down to an abstract ellipsoid. Okay? Yeah, because the ellipsoid will have the sort of the kind. I mean, when you're talking about the resistance to torque, that's all you need actually, and that's all that this is actually describing. So, just as an example, we will take a particularly simple moment of inertia tensor, and just make it 0 everywhere. Just let it be diagonal. So this would actually be kind of an ellipsoid along the axes, right? Where the moment of inertia, or in other words, the resistance to a torque, would be different around, say, the y-axis versus the x-axis. Okay. Now, you can ask, how does this rotate? You basically do the same rotation, the same transformation that you did before, right? Because this is a rank 2 tensor, whether it's symmetric or antisymmetric, skew-symmetric. And what you'll get there, again, only, shall we say, slightly tedious. What you will see in the end is, let's see, you'll get an Ix cosine squared theta plus Iy sine squared theta, right? Then over here you'll have Ix minus Iy sine theta cosine theta, then you get a 0, fortunately. Right. Over here you'll get pretty much the same thing, right? Ix minus Iy sine theta cosine theta. Then the other diagonal element will be Ix sine squared theta plus theta plus Iy cosine squared theta. Again, a 0. And then this will be a 0, and Iz, okay? Because obviously rotating around the z-axis, you're not actually changing the way the z behavior works, or the z-axis behavior. Okay, now, what are these structures? Well, rephrasing this just a little bit, you will get, and pulling apart in particular, the thing that we notice, actually, is that all these angular dependencies, right? That guy looks like your double angle formula, right? So that's like sine 2 theta. And these guys also, can be reduced down to double angle formulas. So let's just pull those guys out. So I have 1/2 Ix plus Iy here, plus 1/2 ix minus iy, and that will be multiplied by cosine 2 theta. Okay. This element here is going to be 1/2 ix minus iy sine 2 theta. And of course, you're 0. Same thing here. Ix minus iy sine 2 theta. And then here I have to write just a little bit smaller. Sorry, it's ix plus iy. But in this case now you'll have minus 1/2 ix minus iy cosine squared, cosine 2 theta. Then you'll have a 0 and a 0 and a 0 and still your iz. Okay, so now we've made more explicit the fact that you have these 2 theta, all your theta dependence is now in the form of 2 theta. So what you see here is that you actually have two things that go on in this rotation. Okay? So so first of all, there's the trace of this matrix, which is simply ix plus iy plus iz. And this is a scalar invariant. Okay? Then on top of that, you have all the 2 theta bits, and what you will see there is that if you rotate theta by, say, pi, okay, not 2 pi, you get the same tensor components. Okay? So, and this kind of makes sense because, if you think about that moment of inertia ellipsoid, right, if you take your rigid body and you turn it over, it doesn't change the resistance to the rotation around that axis. Okay? So what we find is that unlike vectors, where, for a vector, you have to turn it all the way through, your 2 pi angle to get back the same vector. In this case, if you just rotate by 180 degrees, you will get back the same geometric quantity. Okay? So this is kind of a different rotational behavior, which we will talk about a little bit more in just a little bit. And I'm just kind of wondering, is there something else that I'm supposed to be talking about at this section? Okay. Right. So we have various objects. Now it also seems that they have different rotational properties, right? Some stay the same, some rotate after 360 degrees, get you back to the same thing after 360 degrees, some go back after 180 degrees. So any questions about the sort of physics tensors so far? Yeah?
When you talk about the trace here, would that be contracting of the method? Because it's not, the 2 indices have the same variance. So you can't just contract the method.
You cannot just subtract the metric. Oh, contract.
To get the trace of the I, would you not need to contract with the method?
If you wanted to make, if you wanted to, let's see, how does this go? Wait, does that actually work? Are you saying that basically we'll do this? That is the right calculation. Yeah. Okay, good point. Verify that for exercise, and if it doesn't turn out to be true, let me know. Okay. Right. We'll take a quick break. Right. So you can put your pens down. Now I said that I was going to go back into 5D space for a little bit. Okay. So I showed this slide last time about this rather clever Kaluza-Klein idea about having a tightly curled up fifth dimension. There was another version of this that actually came out, some 25 years ago now, which, to me actually seems like yesterday. Sorry. So having a tightly curled up fifth dimension is not the only way to make it difficult to interact with. Okay, you can also just impose some other geometry. And so these guys, Lisa Randall and Mr. Sundram, I can never remember his first name because it's hard to pronounce, they came up with this other kind of clever idea where they said, instead of wrapping it up in a little circle, let's just make it extremely warped. And you basically, in the metric, you would actually see a little exponential factor in there as you move farther. Well, actually, that's sort of like seen right there. And here, what then happens? Again, this is all connected with this question of why is gravity so weak compared to all the other forces. And the point here is that this kind of geometry would then enable you to sort of have all your sort of standard model particles stuck on this part of the world, right? And then you would just kind of leak all your gravitons, all the gravity carrying particles into this bigger bulk universe. Okay. Now, when you read this paper, of course, say, well, how natural an explanation could this possibly be? Why in the world would we ever get this kind of geometry? And I loved it back in '99, reading the original paper. The only sentence, and the sentence that would get repeated in all sorts of papers about this kind of geometry, they would say, such configurations of space and time are known to exist in string theory. Okay, that's as natural as they made it at that time. Now it actually turns out that some years ago they did actually figure out a more aesthetically natural way to argue that such things could possibly come up. So if you hear people talk about string theory and the landscape and throats and sorts of other kinds of things, this is what they're actually talking about. Anyway, one of the other funny things about this is that we talked last week about the fact that you would have these resonances that would come up because you would have excitations through that tightly curled up dimension. In this case, you still get resonances, but instead of being evenly spaced, which you would get with a nice circular topology, you would get resonances that are spaced along the roots of a Bessel function. Okay. So I had a lot of colleagues who then said, wonderful. We can now tell between Kaluza-Klein geometry and, say, the Randall-Sundram geometry, because clearly, if you see this tower of resonances that are spaced along the roots of a Bessel function, this is the smoking gun for a warped geometry. This is why you should never really completely believe theorists, okay? Because this is obviously really artificial, okay? I mean, it's a nice model. It's one of these things where you're just exploring what the implications should be for this kind of idea. But the idea that if the geometry is this kind of dynamical thing, which is kind of at the root of general relativity, why would you expect that this would be that this very sort of constrained geometry would be the only description? Okay. So if you expect the geometry to actually be sort of, just more dynamic and interacting with things, you would almost certainly not expect a purely warped geometry up there. And so, of course, that'll ruin your Bessel root spaced resonances. And so therefore, those of us who went and looked for this just said, let's just find some resonances. We'll figure out whether they're Bessel spaced or not later on. You always try to get your experimental signatures to be more generic than the theorists tell you, because otherwise you'll just be looking for actually the wrong thing, probably. Okay, anyway, so that's our little recreation for today. Right, any questions? Have you guys thought of any questions still regarding 3 dimensions? Maybe 5 dimensions, there are too many questions about, so we'll deal with that some other time. Okay, right. Well, in that case, now let's change gear a bit. On the sort of, the thread of light topics, we are now, since we've now sort of exhausted geometry, at least as far as 3D is concerned, we are now going to talk about groups. Okay. Now, yeah, I know. All the guys who are mathematically inclined are kind of really excited. Now, the bad news is that B2 is not actually a group theory course. Okay? There are only a few elements in the syllabus that actually refer to group theory, and in some sense it's more to be familiar with things in group theory and just see why it sort of comes up. The amount of serious group theory that you'll have to do, fortunately, hopefully not that much. There will be fairly basic things. But we'll try to map that out. Okay, now, first of all, why do we talk about groups? So first of all, let's recall a symmetry. When we talk about symmetry, we require a transformation and something which stays the same. Okay? Now, what we've sort of done in the last week is talk all about this. Okay? Because this is where you have your scalar invariance, you have your vectors, tensors, as well as, all the relationships between them, which will include equations and possibly, greater than or equal, just basically, relationships. Okay, I should probably write that down. Okay, so we've sort of, spent last week talking about this. So this week, we are going to talk about the transformations themselves. Okay? And this is where we actually need the language of, this is where we need groups. Okay, so let's talk about some definitions. Right, so let's just mark that out. Right, so this is a definition. A group is a set G and an operator, which we'll just give as a little dot, such that it has 4 properties. So first one, which is oftentimes called closure. So that means for every A and B, so 2 elements that are an element of G, then A dot B is also an element of G. 2, you also have an associative properties, associativity. Okay, and that is for all A, B, and C elements of G, then you have A dot B, doing that first, followed by the operation with C. Okay, that's going to equal A dot B dot C. Okay. Third property, this is where you call the existence of the identity element. So there exists an element which we oftentimes just call E, which is an element of the set. Let's see, such that for all A, you have the relationship that A dot E is equal to E dot A, which is equal to simply A. Okay, and the fourth one is the inverse element, or inverse elements, since there are more than one. So inverse elements for all A, there exists another element which we will call A, well, A with the -1 there, okay? such that A dot A inverse is equal to A inverse dot A is equal to the identity element. Okay. I should note that in the typed notes, which I managed to put up on Canvas, there is a small error, which is that in writing down the axioms, I just said A dot A is equal to A. You actually do need the A dot E is equal to E dot A is equal to A, okay? And similarly with this one, okay? So I'll have to correct that a little bit later on, that'll come about at some point. But I'm just noting that little omission, okay? Okay, so let's do some, actually before we talk about examples, it's kind of worth looking at these axioms and just seeing how they may be related to symmetry. Right, because, we talked about the transformation, something which stays the same. You can kind of, already see that in the sense that, the A and the B, the elements of G, these are the transformations. So you would expect that if you can do two transformations, you can also do a combination of the two transformations. Okay, so that one seems fairly obvious. This guy's just sort of the order in which you do the transformations. This one, what's an identity transformation? Basically doing nothing, right? Good. And then the inverse just implies that if you can do a transformation, you can also transform the system back. Okay, so it's nothing threatening in this. This is why sometimes people call group theory the mathematical version of common sense. Okay? It's all right, nice and easy. Okay, so let's now talk about some examples. So, let's say, so here's one example. G is simply one element, the identity element. Okay? So, right, does it satisfy all four? Right? Well, actually, the only thing that we kind of have to worry about is, actually, the identity element, that's pretty much satisfied by definition. Inverse element, well, the identity element is its own inverse. Okay, E dot E is going to be equal to E. So this guy is a group. And you might say it sort of trivially satisfies the axioms. And you can say, why did I write that down? Well, it's always good to start simple. Another one, which is a little bit like it, is this one, under multiplication. Okay, clearly it's a group under multiplication. If you try to do this with addition, of course, it would not work, right? So you always have to specify that operation. Similarly, you can go with, say, G is equal to the set of integers. Okay, and this one is under addition. Okay, in which case the identity element is 0, and the inverse is obviously, if the inverse element of m would be minus m, right? That's fairly easy. How about also the real numbers? Okay, this one also under addition. Okay, is pretty clear. How about under multiplication? Should real numbers be a group under multiplication? Got a couple yeses, got a couple no's. What's the one which sort of makes you question it? Zero is not invertible. Okay, so easy solution: get rid of the 0, right? And then it's a nice group under multiplication. But the real numbers itself is not actually a group for that reason. Okay, then there are matrix. So these are examples with nice numbers. There are also matrix examples. Okay, so sets of matrices, like let's say if you took all n by n matrices. Is that actually a group? Well, not exactly, because they actually have to be, right, so not a group, because of course not all matrices are invertible. But you can define all invertible n by n matrices. Okay, and we oftentimes will call that the general linear group of order n. Okay. Then there is also the unitary matrices. Well, actually, I should really not call this a group yet, because we'll talk a little bit more about what's the difference between a matrix and a group element. But unitary matrices. So yeah, that's and this will be like U of n, right? So that's how we oftentimes designate the group. And usually what that'll mean is that it'll be the group elements will be unitary matrices like this, such that U, with the conjugate is equal to the identity matrix. On top of this, there is a subset of this, also called a subgroup. When a subset is a group, it's oftentimes just called a subgroup. So we'll call those the special unitary matrices. So SUN, and that's just that determinant of U has to equal +1, right? Because this one this one allows you to think of determinant being -1 as well. Okay, and then finally, at least for now, we will have the orthogonal group, or orthogonal matrices, right, where you have O transpose O is equal to the identity. And along with the special orthogonal. Okay. Now I should mention that something that should be a little bit obvious when we're talking about n by n matrices. In general, for group elements, and you can see it, in these cases as well, A dot B is not equal to B dot A. Okay? In other words, the commutation relationship for the operator is not guaranteed. And in fact, for U, say 2, this is certainly not the case, okay, or O2, or, actually, O2 is fine. O3, okay, you will not actually have commutative, the rotations are not commutative. So this is actually called non-abelian. Fine, to start off with that, because actually, if A dot B is equal to B dot A, then we have what we call an abelian group. Okay, so groups like U1, I think SO2, you can actually, you can switch the order of the rotations, and it doesn't actually matter. Okay. Right. Okay. I think tomorrow we will get a little bit more into the specifics of the structure of these groups, starting with the permutation group. But just any questions on the just sort of basic definitions so far? Yeah.
The first group, what's the operation?
Sorry, what?
The first group is just E. What's your operation?
Pretty much any. Well, just call it multiplication, right? And because all it is, it's just identity element for whatever operator it is. Yeah. Second question? Sorry, can we just be quiet just at least for one more question, and then we'll begin.
Doesn't
Sorry, the closure implies. Implies what? Oh, implies 3. Well, you need 3 in order to even define 4, actually, right? Because until you have an identity element, you can't really talk about it, about something being equal to it. Okay, yeah. Okay, so we'll finish there for now, and yeah, if you have any other questions, please come up.